Hello. Well, there is main focus on perturbative approximation. I would like to talk about non-perturbative, very basic and promising approach. So instead of going beyond standard model, you would like to go below it. So literally having some Feynman diagram, you'd like to ask what is the field configuration hidden, represented by this Feynman diagram, especially in electromagnetic field. So for electromagnetism, the main point we like to repair is the electromagnetic lack of charge quantization. Is the standard Gauss law, Return charge being any real number, while in nature it is integer. To repair it, we can use the Gauss-Bonnet theorem instead, which says that integrating curvature of some deeper field of n here as electric field, we calculate the topological charge of this deeper field, so which is quantized. Yeah, so just interpreting curvature of deeper field as electric field, we get electromagnetism with built-in charge quantization. I will talk about. So the basic Lagrangian I'm considering is this one, similar to electromagnetic Young-Mills, with F mini, but with F being a curvature of some deeper field. So the big question is, what is this deeper field? The simplest one is just vector field, when this topological charge is, for example, Hedgehog, elementary, but it's definitely insufficient, so I will use a bit more complicated, called Landau-de Gennes field used in liquid crystals. But in every point, we can imagine there is an ellipsoid, mathematically represented by tensor M, which prefers some set of eigenvalues. So the eigenvectors are the axis of our ellipsoid in given point. Our eigenvalues are the kind of shape, are the parameters of our model, which are required to recognize various types of interactions. Okay, so let me briefly start with one-dimensional model, so-called Sine-Gordon model, which can be realized with lattice of pendula. So we have pendula want to be gone down, but there is also down to pi farther. Yeah, so we getting this simplest, stable, minimizing energy configuration called king, behaving as particle. There is creation of such pairs, annihilation. We have massless wave, for example, from annihilation and massive particles. Also, the entire special relativity is here. So this is a very, very good model to start with particle physics and special relativity. But finally, we want to go to three-dimensional and maybe four. So in three-dimensional, we have basically three types of topological defects. So one is domain wall, but we can, in particle physics, they are not existent, and we can avoid them, for example, with this field of ellipsoid when rotating by pi is the same ellipsoid, so the domain walls disappear. But we need these two, so the point-like charges, which we are calculated by the Gauss law, and which get Coulomb-like interaction, so as electric quantized charges. Also, the topological vortices are crucial, and in particle physics, they correspond to so-called quark strings, connecting quark, anti-quark. Yeah, so to understand quark, we need both. So there is topological vortex, and we perform some this inward rotation. So if it's by pi, then we make a hedgehog, and hedgehog is elementary charge. But we can also perform a fractional rotation, getting like here, like quark. But there is some conflict, and in QCD, this conflict should have like 1 gigaelectronvolt per femtometer, getting both the Coulomb interaction, but also this linear dependence for asymptotic freedom and confinement. So this is called corner potential. We go further. Also, in LHC, that there is this basic model called so-called string hadronization, that they assume that they created this one-dimensional structure, this quark string, and it decays to particles. So what we need to do is just to find a correspondence between what topological vortex can decay into and what they see in particle physics. What leads to very simple and promising correspondence. Okay, so in liquid crystals, they go in this direction in the best journals. So, for example, the Coulomb-like interaction, that having two topological charges and in some distance and waiting sometimes, they get long-range interaction similar to Coulomb. And recently, even going to vortices, knots of these vortices, and knots of vortices of various size seem similar to nuclei, and I will talk about this similarity. And indeed, in this recent paper, Nature Physics, that they get this fusion fission as nuclei with baryon number. So this starts resembling the nuclei. I will show further. Okay, so here is this this quantized charge Gauss law, that using this curvature instead of electric field, we get integer number. Yeah, so mathematically, this Mathy-Fabers approach, that we have some deeper, let's say, unitary vector field n, we define its connection, which corresponds to a field, and curvature corresponding to this F tensor, but this is dual F tensor. So using original F tensor, we will get magnetic monopoles, but if you go to dual formulation, they become electric monopoles. So thanks of going to this dual formulation, what is also common in QCD, we get only electric monopoles, not magnetic monopoles. Yeah, so here are some pair creation. For example, for virtual pair creation, we could start this process, go here and go back. So we can start this process if we don't have energy to create the pair, but still we have some perturbation or pair creation of vacuum. Okay, so here is a simple derivation with code in Mathematica of Coulomb, that we start with such ansatz. For here are the opposite charges, here are the same charges, and we calculate energy by integrating Hamiltonian. Yeah, so here is this integration, and here is the points are numerical results which agree with 1 over distance, Coulomb interaction, attractive or repelling, and the line is fitting this Coulomb-like dependence. We can see it's practically perfect. So, however, there are two weaknesses in this calculation. So one, there is cutoff in this integration, and second is there is ansatz. So we should do it better. If we don't do this cutoff, we will get infinite energy. So now we need to regularization, the second problem, that in center of charge there is infinite energy, and it is also resolved here, but by using this Higgs-like potential. Yeah, this, for example, the standard Higgs potential would prefer unitary vectors, but also would allow them to deform into zero vectors. Yeah, so we would get this kind of configuration for Hedgehog. Without regularization, we would get discontinuities in the center, which has infinite energy. So now we define this connection as a field, curvature as F tensor. But now there is this problem, this infinity problem. So if we integrate the energy of electric field of charge from 1,4 femtometer, then we get mass of electron. So it means that we need to deform in this kind of scale. And the proper calculation, like here, but with optimization and with regularization, leads to this kind of Coulomb behavior, that in very small distance, like 20 femtometers, it's quite steeper. The behavior is quite steeper. So that means that Coulomb force becomes slightly stronger, and this increase of Coulomb force in very high, very low distance, very high energy is called the Rani-Kaplan effect. That alpha grows in very high energy. So and Faber gets this kind of behavior. So from regularization. So we should. So this is a way to see this deformation, that perfect point charges wouldn't have this deformation, but here we get them, and they correspond to this required regularization. So electron is point-like, but we've required the deformation of this perfect point charge. So maybe very briefly some similarity with arguments of the size of electron. So one is Delmert, but he's shown he assumed he showed proton as made of 3 quarks, citron as made of 3 nucleons, and try to draw electron as made of 3 partons, and probably started with line, but getting negative radius. So here is radius, here is G factor -2. So he extrapolated from 2 points with parabola. We cannot do it, so it's a nonsense argument. So let's look at more serious arguments. So one is running coupling, and we get the agreement. And another is that is electron-positron cross-section, that looking at this energy, is huge energy. In log-log plot, we can see there is most linear behavior. But we are interested not in scattering of high energy particles, but in size of the resting electron. So we should extrapolate this line to the resting electron positron, and doing so, we get like 100 millibarns, what corresponds to like 2 femtometers. So what is in agreement with this size? We need to deform perfect point charge, not to exceed mass of the electron. Okay, so let's go further to this vortices. Yeah, so we have they have quantized magnetic field, for example, in superconductor, and asking what is this a quark string between quark and anti-quark. They also non-perturbative approaches I have seen only as topological vortex. So as mentioned, we have topological vortex. We perform this fractional charge. So we go toward this hedgehog, but not entirely. And it leads to some conflict, which should have linear dependence, one Gauss per femtometer QCD. So finally, we get this first Coulomb interaction, but then finally there is linear dependence, corner potential required both for quark confinement and for asymptotic freedom. Okay, so the question is, are there topological vortices in a vacuum? So there are many arguments. I'm talking in a moment about halonuclei, that there are these nuclei like lithium-11, that there is a core, and there are like two neutrons in very large distance, larger than of nuclear force, and somehow they are stable, like for milliseconds. The question is, what binds these two neutrons? And I haven't seen any other explanation than by just these are topological vortices, the quark strings. And a very nice example, so there are some cosmic examples that I see these filaments of galaxy, one-dimensional structures, and also just photos of sun's corona. There are these shining lines, so in vacuum, and they are very stable, and they don't understand why they are stable, and topology is the only explanation. So we need these one-dimensional structures in various scales. Okay, so let's go to this example of halonuclei. Yeah, so lithium-11, for example, there are a few of them. Can be one or two protons or neutrons, so can be protons also. And still there are very stable, like hundreds of milliseconds. So again, so the question is what binds them? Also, they need three body forces, and they call it Borromean. That if you remove one of these neutrons, it will fall apart. Yeah, so again, what binds them? If you're looking for a nuclear force, it has minimum like 0.8 femtometers, but they're a few times larger. So assuming that there is literally some one-dimensional structure, this quark string going to them, would solve them, would both get the stability, require three-body forces in effective descriptions, and could be this Borromean. Yeah, so this is one of many suggestions that we should imagine nuclei as vortices of quark strings, topological vortices. Okay, so let's think about what is a baryon. If nucleus is a knot of the quark strings, then the baryon is the simplest knot. Yes, and this is the simplest knot. So one vortex inside and second vortex around. So with this view, let's think. So here is cross-section for proton and for neutron. So for proton, what's happening? So for proton, we can see that this external vortex, it deforms the structure of internal vortex, and deforms it exactly toward hedgehog. And hedgehog for us is charge. Yeah, so proton can just enclose this hedgehog. But neutron also has this partial hedgehog, but it has to compensate it. And this compensation is costly. Yeah, so this way we get explanation why neutron is heavier, because both baryons have tendency for charge. A proton can just enclose it. Neutron has to compensate it. Yeah, so also we can ask why there are 6 quarks, because there are 3 types of vortices along one of 3 axes, and sometimes there is this vortex around, sometimes there isn't. So if there is plus 2/3, if there isn't minus 1/3. So the U quark can be lighter because of this satisfying this interaction between two vortices. And generally, it is known that by proton has only positive charge distribution. For neutron, there is positive core, negative shell. Yes, and we get it, positive core, negative shell. Okay, so here is this positive core, negative shell. And so here proton, neutron. And let's now let's think about the deuteron as the simplest non-trivial nuclei. So here we have 2 baryons, which both of them have this tendency for charge. So we have plus, minus, plus. Yeah. So this way we can see that deuteron has to have electric quadrupole moment. Yes, plus, minus, plus. And experimentally, indeed, deuteron turns out to have relatively large electric quadrupole moment. So naively, if you think about proton and neutron, it should be 0, but experimentally it is positive. And so it is resolved by saying that there is S and D orbital and just fitting to the experiment. So the mainstream doesn't seem to understand this quadrupole moment, while here we can just draw a picture and get explanation why neutron is heavier, why deuteron has a quadrupole moment. Okay, so now I mentioned this about this three hadronization, yeah, so that they assume that in LHC collisions there is created this hot quark string and it decays into particles. So we need to think about what topological vortex can decay into and try to compare it with what can be obtained in LHC collisions. So we always can get these closed loops, and they are very light and stable, and there are many arguments they agree with neutrinos. So there is proton neutron. Also, we could get this additional twist for such loop, and it seems in agreement with strangeness. So usually, if you have strange baryons, they usually go to one lower strangeness plus pion or kaon. So so this kind of picture seems to resolve this strangeness decay. And for neutrino, so for neutrino, we need to think about beta decay. So in beta decay, we start with neutron, and it becomes proton and releases energy, part of energy as gamma and electron, and part of as this neutrino. Yeah. So if there is quark string, it can form this closed loop, and it can carry part of energy and will be very light and stable. We get three types because it is along one of the axes. We can get oscillations between them. I have some mechanisms for the propulsion. So, uh, so, okay. Okay, so here is a summary. So in three dimension, we can get this hedgehog as elementary charge of one of the axes because of living in three dimension. We have three leptons, three neutrinos. There is Herible theorem that trying to align the second axis on the sphere, we cannot do it. So there are no naked charges. Leptons also require the spin, magnetic dipole moment. So then there are baryon, the deuteron, strangeness. And for the end, I would like, so here is the local dynamics of our M field. So there is local rotation of the field and boost, and we have these various types of interactions. So there are high energy tilts for electromagnetism, low energy twists for quantum mechanics, for example, in QED Lagrangian, and there are also boosts. So we can also get Maxwell equations for gravity. There are also interactions between them. So also automatically we get gravity. Okay, and here is the last slide for summary. So the question is what we could do further. One big question is how to get the oscillations. For example, that why electron has magnetic angular momentum, magnetic dipole moment, why neutrino oscillate. So there appears this kind of mechanism. For example, here is for one-dimensional situation that activating energy particle can slightly reduce its mass. So you can get electron like this. For neutrinos, why electron has angular momentum as linear angular momentum, so something rotates, but this is not a point. This is an actual field around, so actual field to rotate. For neutrino, this rotation is not restricted to a plane, but this is full SO3 rotation. And it turns out that it can be SO3. For quarks, we can get this quark potential, but the most promising is going toward models of nuclei, which, for example, there is this halonuclei. We could try to understand this way the EMC effect that the quark structure of nucleus is quite different than of nuclei already for deuteron. So finally, this might bring to practical ways for optimization of fission and fusion. So thank you.